Hello and welcome to looking at SimSolid. So today within this video what I will be doing is taking you through knowing how to set up a basic linear static analysis. So to begin with, SimSolid itself is a CAD agnostic software. So what that means is if I were to say import a file, you'll see what's nice is that you can read all of your different CAD in its native CAD format, so you don't need to particularly export it into a specific format, you can bring it in its native format. So upon starting this demo, say if I were to bring in my assembly, so here I have a parasolid, if I double click to bring it in, you can see by default SimSolid has recognised that I've got more than one part, and what's nice is that because there's more than one part, it will know for a fact that we need to establish connections and contacts between all of them. So you get a default automatic connections box that gets popped up. And what you can do is insert different values for gap. So say if any part that has a gap of 1 mil between one another, or if there's penetration or overlap of parts that have a 1 mil tolerance between each other again, then this is where we're effectively establishing all of our different connection points and contacts. So if we were to just specify those two values, just click OK, you can see by default it's made all of our different connections for us. So if we wanted to view all of them, then you can see exactly where those different contact conditions have been established and the contact type as well. So SimSolid's really intelligent in that if you were to bring in bolts, nuts and washers, there's a geometry featured recognition tool inside of it, in that it will recognise where your bolts are, as well as where it then gets connected to the nuts, or you'll be able to see that based upon what you have and the part of your bolt, it gives it different contact conditions. So on the bolt shank itself, it will know it's sliding in those areas, but at the bolt head, it will be bonded. So if we just look at SimSolid itself, you'll see that we have all of these different options. So we have the main toolbar at the top here, and we also have a secondary toolbar down the side column here. So if we start by looking at the different options that we have, obviously you have your different file organization tools. Let me draw a proper box instead. There we go. So from here we have all of your different file organization tools where you can save a file, start a new project, etc. With this part here as well, you have all of your different views and your icons. So based upon the views that you have, obviously you can specify to fit everything to page. You can expand your window, you can zoom in, and you can also look at it from different perspectives, so from the XY plane, ZX plane, etc. Once you orientate your model in different views, you can actually save it so that it's always saved as a view in itself that you can refer back to. So if I were to just specify, you can do your user defined views, and you can see from here, you can look at it from right, left, top and bottom, etc. as well as isometric. But say if we've orientated to this specific view here, we can always click on plus and click add, and you can see that this is always a view that you can go back to. So if I go back to here and then click on view 1, then you can always bring that view back. Along the rest of this bar here, you have all of the different sort of visualization tools that you need to see your different parts. So you can make it with the wireframe, so you're looking at the edges. You can specify all your parts in different colors, so you know exactly where they are. You can make them transparent, and you can also implement a cut cross section as well through it. So you can see through it all, and you can rotate it around to reach other areas. And of course, if you just need it back to its default, you can just assign everything back to how it used to be. What's nice is that you also see we have a live synchronization between your actual assembly and the graphics itself. So if I was to click on any of these parts here, then you'll see it updates itself and it will show you where it is within your assembly directory. And like we said before, because of the geometry feature recognition tool that it has built in, you can see all your different bolts and your washers, and it automatically selects wherever you've selected within your assembly tree. If you were to right click in any of these areas here as well, you can specify exactly what it is you want to show. So you can show it via just the bolt itself, or you can show via just looking at the nuts as well. Within SimSolid you have a built-in material database, so by default there's already a material database within here, but of course you can always define your own by importing in your own material database as well, or your separate material cards that you need. And what's nice is that whenever you select on any of these materials, you can apply it to just the parts that you've selected, or you can apply it to all as well. So within this study, what we're going to do is just make sure that we apply steel to all of our materials. And this time you can show via materials, so say if you did have a big assembly where you have multiple different materials, you can then show via a material type. So you can see everything on screen here. All of my parts are made of steel. Now what you also see is a final note. If you were to click on any of the parts here, if you right click on them, you can see everything that's associated to it as well. So obviously you have all of your different view icons, so you can hide it, suppress it, etc. Just to note, you can suppress a part away from the study, so what that means is it's been excluded out of your design study itself, but it hasn't been deleted from the overall model, it just hasn't been counted in for. So that's the difference between suppressing a part and deleting a part. Obviously you can zoom into it, so you can see exactly where your different parts are. But then if we carry on going through the options, if you were to right click, you can then specify exactly how it is you want to look at the type, the material connections, and the part connections as well. And obviously you can look at all of the information around it. So it'll show you exactly where the centre of gravity coordinates are, its bounding box, volume, area, etc. So after we've actually established all the connections and we have all the right parts with the right materials assigned, what you will be able to find is that obviously based upon where I click in my project tree, you'll see that this secondary toolbar changes. So if I was to click on assembly, you'll see that this is where you can access the material database. You can start reviewing all of your different parts as well. You can set part rigids. You can create a liquid body, any sort of axis system as well. So by default, obviously you know that this is our global axis, but should you need to create any sort of user-defined coordinate systems for local axis systems, you can. We have what we call spots, so you'll see that when we do select a face, occasionally for this whole beam say itself, you can select the whole face, but say if you only wanted to apply pressure on a certain area, with spots itself what you can do is make sure that you draw a square or implement a sort of section area where you want to implement your boundary conditions onto. We can go through that in the example later when we set it up for a linear static analysis. You can also create line on parts, and obviously when you bring your CAD data in, you want to check to see if your CAD is all perfect. You can then review your different parts itself, so you can see the volume and the relative volume. So if you have any sort of slither volumes in itself, you can see what it's like based upon its relative volume. And obviously you can check for any sort of geometry defects, so if you have any opened edges or parts that aren't connected up properly when being drawn in CAD, obviously if you don't have any defects then it will tell you no defects are found in geometry, but you can check for any sort of part overlaps and self-intersections as well. You can also review the similar parts, so with reviewing similar parts it will tell you the different washers you have, the different bolts, and obviously based upon the size of it and the grade that you're using, they'll put them in separate categories. Now you'll see that when we click on connections, this is where we can establish all of our different contacts within our analysis. So you'll see by default when you bring parts in, you can use the automatic connections panel. If that doesn't pop up for you, just click on this top button up here. Obviously we can then actually manually add in different contact conditions as well. You can do it via a master connect, so selecting the one master part and then all of the other surrounding parts to it, so any mating parts of it, you can select them there. Or better yet, you can do a group connect, so say if you just wanted to establish a connection between this part and this part down here, so between the three of them, then you can specify the tolerances again to establish a connection between them. And all you need to do is click Find Connections and click OK. But obviously we already have all of our connections established here, so I don't need to go through and do all of that again. If you want to incorporate any sort of welds, you can create spot welds, seam welds within SimSolid. You can also create adhesive connections from the solids itself, so if you already have your adhesives drawn up, you can specify different solids being adhesives. And obviously, better yet, you can actually also implement any sort of virtual connectors. So if you need to put a sliding or bonded pin between two parts, a general connector to just connect two faces together, or remote support. So if you know your part is being supported from a remote distance, so remotely distanced away, you can implement a remote support. All you would need would be the coordinates and obviously the contacting faces that's being supported on. Any bushing you want to implement, rivets, remote masses and joints, then you can use the virtual connectors. What's nice is that when you are working with a huge assembly of parts, if you want to make sure everything's connected, you can check for any disconnected parts as well. So currently here we know everything's connected properly because our assembly has no disconnected group of parts, but should you have any, it comes displayed in a really nice table and it will show you exactly which parts haven't been connected to the rest of your assembly. And obviously afterwards, once you have all your connections, you can review all of your different connectors as well and go through and see which ones they are and the different settings that were set to it. So now that we have everything that we need, so we have the right parts with the right assigned materials and all of our contact conditions, we're going to take it through for an actual analysis. So in this case, obviously at the end of our toolbar here, we have a few more icons. Now, the massive question mark might have given away that this is where you can go to access any sort of help pages and extra tutorials, but the front four icons here, this is where you can start looking at the different types of analysis you want to specify. So SimSolid's capable of doing a structural analysis, whether it be a linear or non-linear one. You can then start looking into dynamics, so you can start requesting for the natural frequencies and conducting a normal mode analysis, so you can see the natural frequencies of your parts. You can also take it through for dynamics, so within dynamics you can look at a transient or frequency response and random response analysis, and you can also conduct a thermal analysis. You just need to make sure that you have all the thermal properties within your material cards. So for this tutorial we're going to set up a structural linear one. Now you'll see the moment we specify structural linear, it comes up with a new section within your design study, and you'll see a whole new plethora of buttons for the secondary toolbar. You'll see within this section here, so this top area, the top four icons, they represent your different constraints. So you can specify an immovable constraint, a slider support, a hinge support. Obviously, an immovable constraint means it's constrained in all degrees of freedom, so it cannot translate or rotate in X, Y, Z. If you're specifying a slider support, that means it's free to translate in 1 degree of freedom. And obviously if you specify a hinge support, then you're enabling it to rotate around 1 degree of freedom as well. So say if we were to specify a movable, for now within this example what we can do is you can apply it to a face, an edge, a vertex or a spot. For our tutorial we'll just click on these two faces at the side here and the front here. Obviously as an example, if you did select the wrong face, you'll see a delete button. You can easily just delete it off. And you'll see once we specify some supports, you'll see there's some yellow crosses on them to show where the supports are. Now on the next part as well, like we were talking about, say if we actually wanted to only specify a certain area on our beam to not move, that's when you can create a new spot. So by default, if I was to select on any face here, I can specify a rectangle, a circle, a triangular spot, or spot on a cylinder, etc. You can also import more options as well now. But say for example if I want to create a rectangle, I just specify 5mm in terms of my dimensions. Obviously you can see that it creates a very small area, so if I just made that slightly bigger, and if I click OK, you'll see that you can actually apply some constraints to the spot here, and the spot itself is visible within your actual assembly tree. So within the assembly tree you can then locate to see where that spot is. So say if you only wanted to hold a certain part of your beam down, or if you only wanted your boundary conditions to be applicable to that side, then that's where you can specify it using spots. But we won't be needing it in this analysis. This is just an extra bit of information for you. Now on this next part, you'll see that we also have a spring support. So this is like establishing an elastic foundation for, say, if something isn't actually properly constrained, but there is a bit of leeway to how much it can move. You can give that sort of elastic foundation in terms of stiffness values in X, Y, and Z. You'll see for the next section down here, you have all of your different loads that you can apply. So you can apply pressures, force displacements, you can do gravity load. You can also specify inertia loads, remote loads as well. So just how we had remote supports, you can also have remote loads. So you can have a load acting on a part from a distance away, so it factors in all of the moments applicable to that surface. Obviously you can specify thermal loading, bearing loads, hydrostatic pressures, and any sort of distributed mass. If you want to include any sort of pretensioning into your bolts as well, you can do it through bolt tightening or nut tightening. So if you have blind bolts, then that's when you can do it via bolt tightening. If your bolts have a nut to them, then you can obviously preload them with pretensioning using the nut tightening tool. So in this case, what we're going to do is click on force displacements, and what we want to do is apply a force of, let's say, 1000 newtons to the end of the circle here. So keep your selector on face, select the faces that you need. Now this selector is really good in that obviously it's always a fail-safe way of selecting what it is you want to look at. If you have face selected, you won't need to worry about accidentally selecting an edge instead. So if we have that face selected, you'll see down at the bottom options here, you can specify the units that you want to insert your magnitudes in. And what's nice is that although we had the constraints plane, what you can always do is specify a displacement as well. So if displacement is 0 on all of that, then obviously you're telling it that none of these faces can move. So that's another nice way of implementing constraints or guided movement. So say if we're only letting it move, or there's only a force of minus 1000 newtons in Y. So obviously minus because we can see the global axis, it's positive upwards, and we want it to be acting downwards. We want it to be, so we can see positive Y goes upwards, just like that global axis here does. And obviously if we want our forces to be acting downwards on it, then we need to specify it as a negative value. So that's why we put negative 1000 newtons, and if we put displacement of X and Z in 0, that means it will only ever displace downwards in Y. But for this example here, make sure you leave X and Z as actually in force, and we'll assign them with 0 newtons, whilst Y force has negative 1000 newtons. Now you'll see within here as well for solution settings, if you were to double click on it, you can specify exactly how accurate you want it to solve. You'll know that SimSolid is meshless, in quote marks, meshless, in that you don't need to do any sort of meshing yourself. The calculation of the actual results that you get is done through high order differential equations, in that it'll probably see where your areas of high stresses are, and it will put further refinement to those areas. So with the solution settings, if you have objective as adapt for stiffness, that's just looking at the general displacements of all of your different parts, so you can see where the load paths are. If you do it adapt for stress, what this does is it gives it a higher iteration solution setting, so that it refines it refines different high stress areas further, so that you get more accurate stresses in those areas. You can do it custom, so that say if you did want to specify your own adaptive solutions, we'd say the maximum number would be 5 in this case for structural analysis. You can go higher if you're doing dynamics, but say if you have thin solids and lots of features on those parts, then you can adapt it to those. But for now we'll keep it to adapt for stress. Click OK. And just so you know, if you double click on setup, if you did want to turn it into a non-linear analysis, you can do it easily by specifying exactly how it is that you want to make it non-linear. You can do it through its boundary conditions, such as contacts. You can do it via, entering the plastic region of your material curves, so encapsulating material non-linearity. Or you can do it geometric non-linear as well, so if you know for a fact there'll be large displacements. So obviously once we have everything set up, if we just click on this button here, you'll see within a matter of seconds, this is actually currently solving live. and what's really nice is that you get your results within a matter of seconds. So straight away we'll be able to see where, if we were to click on this button here, you can get your minimum maximum stress values coming out. You have your usual play button to look at the way in which your simulation is played. You have 3 different image options as well, so you can look at your contour in discrete fashion, in a slightly interpolated way as well with 12 colours, or you can look at it fully interpolated as well. You can change your oscillation speeds and how discrete or continuous your animation is. This button here also helps specify your scale factor deformation. So if I was to click play, you can see it's a lot more exaggerated and it's done for graphical purposes only. Now by default you always get the same set of results. So you'll always get displacements, stresses and strains, and you can look at your stress contour plots in a form of a factor of safety as well. And obviously that's just done with respect to your materials yield value. You can also change your legend at the top, so your maximum values, if I specify that 20, you can see there's a lot more areas which will exceed the 20 mark, and if we do it to 10 as well, then you can see it done again. But if I just leave that back to 30. Now, for these other options that you see down here as well, so where you see all of the other post-processing options, we have what we call the pick info probe. So say if I were to select a few points here in this area up here, then you can see that instantly they display all of the information attached to those points, and if you were to evaluate the average, you can know the average of that collection of points as well. You can do the same for a face, where if you select on a face it will give you your information that you need. You can also save it as a CSV file for any sort of further post-processing that you want to do in Excel. We also have what we call the result graph. So say if you wanted to understand exactly how your stresses vary over a length, what you can always do is specify the first point, and because we have 20 number of points on this line segment, it does 20 interpolations, and you can see exactly how your stresses vary along that length. So you can see it decreases, and towards this area it actually increases it as well. And obviously you can save this data externally as well. We also have the bolt and nut forces. So what's nice about this is that it gives you a whole table as to what of the forces that your bolts are experiencing. So you don't need to do any further post-processing of calculations itself. SimSolid does this all for you. But should you want to take it out into Excel, you can save it as a CSV file again. We also have our reaction and contact forces. So what this does is it just tells you the reaction forces between your different parts and at your connection points as well. So it gives you all your resultant forces, resultant moments, and yet again you can save it as a CSV file. Now this next part is probably my most favourite part about SimSolid. So if we know for a fact that this was our first CAD iteration design of this beam down here, we know for a fact that we've improved the design of it, and we want to see exactly how our stresses have improved. So you can see currently our maximum stress is occurring around this area here at around 45. And we know for a fact that we've got a new design and we want to change it now. So very easily, just go into project, and what we can do is import from file. If we import our second design iteration, SimSolid very cleverly understands what's changed, where the design changes, and it knows to map everything over for you. So yet again you can do the automatic connection points for the new part that you bring in. So if we keep the same tolerances, click OK, we can now see within connections anything that's in bold would be our new contact conditions, and that's understandable because you can see within this new design, the second design iteration, we have some plates, some reinforcement plates, and some extra bolts and nuts as well. So you can see all of these contact conditions being selected for us, and all we need to remember to do is actually assign steel to the new parts that we bring in. So make sure we assign steel again to all of our parts. We have all our contact conditions that we need, and what's nice is that say if you had 10 different load cases, SimSolid knows to map them all over for you, so you don't need to set them all up all over again. So you can see that within our design study 2, we still have the same immovable constraints at these faces like we set up for design study 1, and we also have the same force acting on that front hole there. So you can see design study 1, if I click on it, this is our baseline study with our old CAD, and the new CAD, and very quickly what we can do is click on Solve again, and within a matter of seconds you can tell exactly whether if your new design has actually improved or you need to look at improving it further. So like I said before, it's currently solving in live time. If you did want to look at how long it took to solve, you can easily right click on results and you can see the runtime for it. But very quickly we can click on stresses, and you can see that, compared to the previous version, so Design Study 1, we had 45 at the top there, whereas now our maximum value is 42 and it's just down here. So overall, we know for a fact that our new design has indeed improved our design of our beams. Now, some of them are really nice post-processing tools. So say if in Design Study 1, because we currently have a still picture, we don't have a moving animation. If I was to click on this camera here, you can see it's taken a photo of our snapshot as well as its view. And if I was to right click on it to save media to file, you can then see very quickly that you can save it as a PNG format. If I change the viewpoint of it, so let's say I look at it from here instead, and it's a playing animation, if I was to click on the camera icon here, SimSolid knows that you're playing this animation, so it knows for a fact to save this media file as a video. So if you were to right click on it and save media to file, you'll see that it'll save itself as an MP4. And what this does is enable for very quick post-processing, so you can see exactly from Design Study 1, we have the name of it down here as well. And if we were to click on the results of Design Study 2, you can see quickly and immediately just how your part has improved. So from 45 megapascals, it's now 42 megapascals in a new location. And the same can be done for your first screen as well. So you can see how within Design Study 1, 45 and 42. And this is effectively SimSolid in a nutshell. So thank you very much for listening. I hope you enjoy using SimSolid. Thank you.